Thank you. Sorry, I have this in my hand now. Thanks. Do I have all the peer review rubrics? Alright, give me a thumbs up on the true false so I can get past that. Okay. You guys like 10 more seconds here. I would like to go to the multiple choice next, so I'm going to skip this up the middle, and then I can go over some of that orally. But it'll give me a chance to see superficially kind of where we're going. Now, on the multiple choice, on my key, it goes in number order. You'll notice I skipped what number is on here. 23, 24, 25. So I'm off by 3 numbers of multiple choice. So the first multiple choice is 20. It says 31, but it's actually 28 here, okay? An alarm keeps going off in this class. All right, so here's 28, i.e. 31. A, give me a thumbs up. I'm just going to go in order. I mean, it's in order, okay? A, B, D, C. And then 35 on your paper, which is 32 up here, is B, C, C, or I'm sorry, B, C, A. So basically I'm 3 numbers off. Are you guys picking this up? Sorry about the confusion. I'll let you guys read it because I don't want to mess you up. Alright, so I'll start on the multiple choice. Does somebody have a question they want to raise, or is this something that you can look at and kind of self-reflect on and see where your mistakes fall?
Yes, 30 is
This 33, so number 36 on there, okay. Standard conditions, so this is STP again. Standard conditions are 1 atmosphere and 273 Kelvin. So what is equivalent to 273 Kelvin? Anybody? 0 degrees Celsius, so then that kind of knocks it down to C or D. And then which of those pressure units is equivalent to 1 atmosphere? 101.3 kilopascal. So what you guys wrote down in your reading guide 14, which is you still have it because we have not reached chapter 13 stuff just yet. You have this knowledge now, just like 1 foot equals 12 inches, which equals 26, 27 centimeters. I'm not quite sure how many that is, but you can do the same thing with pressure units. 1 atmosphere is equal to 760 millimeters of mercury, which is equal to what? 1 atmosphere is equal to 760 mils of mercury, 101.3 kilopascals. And if they ever say anything about torr, it's 760 torr. I don't know what it is in PSI, so we don't use inches in the SI world, but we do in America. But those are all the equivalencies of the pressure units that we'll be working with. How about another one on the multiple choice, guys? Did anybody get something wrong they need clarification on? Okay, how about on the sometimes true, never true up here? Issues with some of the readings? You gotta talk to me. Okay there. When particles of a substance are heated, some of the energy is absorbed by the particle and stored in the form of potential energy. What did you put? You said always true?
Yeah.
It depends on how much kinetic energy that particle already has. So this one doesn't specify as a particle a solid, liquid, or gas. So potential energy is something that particles gain when they're undergoing phase change. Are they always undergoing phase change? No, but they sometimes are. So that's why it's a sometimes true, not an always true example. And so we're going to talk about heat curves in just a second, and it should clarify that. Another one on the true false. All right, so I'm expect that you guys will go back and reflect on that if you're not going to ask questions. Yeah? Okay, so let's switch modes. We're going to go through the rest of the heat exercises, which are on the back of your note sheet from yesterday. Somebody has an example of that note sheet, I hope. Thanks. So we didn't quite finish this little section 2. I'm hoping to spend no more than about 5 minutes here. So we're here on section 2. Do an extra. I'll hit the middle stuff on my own, but I will take that problem set eventually. Not yet though. Not ready yet. Alright, so here's your example of your heat curve from yesterday, right? So we were finishing up looking at, what part did we get to? D or 5? Did you get to 5 on here?
We got to 3.
Oh, okay, so I believe you. Is this A, B, C, D, E, F? Okay, so you guys tell me what's happening from B to C. What's happening from B to C? Shout it out, let's go. Okay, what phase changes it? Melting, because you're going from solid to liquid to gas, or eventually, but between B and C, that's the process of melting, which we also call fusion. Remember that, fusion? Okay, so that's melting, and so specifically, what do you notice here? What do you notice is present? Solid and liquid, because it's transitioning. So at B, it's probably 99.9% solid, a little bit of liquid. But at C, it's 99% liquid, a little tiny bit of solid left, but as soon as it hits the liquid phase, it's then 100% liquid. All right, so what's happening from D to E? D to E. Anybody, shout it out. I'm going to use the word vaporizing or evaporation. Boiling is a specific term, but you can see it's going from liquid to gas. What do you notice is up here? Yeah, both gas and liquid particles, and so that's why they're in physical equilibrium. They're kind of both present, but eventually, as they continue to add heat, so much heat's going to cause them to 100% phase change to form their gaseous form. How about from from C to B? So why freezing? You're in the opposite direction. From C to B, the opposite direction means you're going from liquid to solid, so it's freezing. E to D? Condensation, good, because you're going the opposite direction. You are condensing the gas into liquid form. Which of those is an endothermic change? C to B or E to D? Endothermic. Endothermic means what? Taking in what? Which of those are doing that? Oh. Say again? Which is endothermic? This one going from E to D or C to B? Nobody? Neither of them. Okay, sorry. Neither. They're going the same direction. One can't be endo and the other one be exo. Neither of those are endothermic. So both of these are an exothermic change. We're going from a high kinetic energy gas to a lower kinetic energy liquid. They're releasing energy, exothermic. High kinetic energy liquid to a lower kinetic energy solid. Both those are releasing energy. Just kind of see if you have some critical thought about you there, okay? How about, at which point does the substance begin to melt? A, B, C, D, E, F. Where? B. It begins to melt at B, right? It begins to melt there because that's where they transition from solid to starting to form liquid. Where does it begin to boil? Where does it begin to boil? D. Okay, thank you. Where does the substance begin to condense? E. Good, because that's the transition from gas into the phase change. So it's at this very end of it. What is the freezing point? Say again? Oh, on your graph it's different. I was like, how do you guys know that? Okay, so you're looking at the freezing point. At what point specifically? At letter C, which is at the 290 Kelvin mark. Good. Melting? 290 Kelvin. So the freezing point and the melting point is the same temperature? Yes, that's what you just said, right? It is. Look, I mean, it's at the same point. So if that right there is where solid turns to liquid, but it's also where liquid turns to solid, it happens to be the same temperature, and that kind of makes sense. It just depends on which direction you're going. So it is the same temperature. In your graph, it's 290 Kelvin. So melting point and freezing point are the same temperature because it's the same interface of transitions of phases. Describe the actual physical situation the graph might be representing. I'll let you guys do that in a second. But before I move on, this is the last point I'll add about heat curves. So you notice we've been talking about temperature differently than heat, right? So they're not the same thing. So where's the temperature staying constant, and at what point, like what's happening at that time? When is the temperature constant? During the phase changes, which are where on the graph? The flat sections, also known as the plateaus, or horizontal ones right here. So the temperature is constant there. How in the world is the stuff changing phase? Because we're going from solid to liquid, and we're going from liquid to gas. Doesn't it seem like this low kinetic energy to medium, and then medium to high kinetic energy, doesn't seem like the temperature should be changing with it? Say again? So the potential energy begins to change, though the kinetic energy is not. So remember, temperature is actually more of a measurement of kinetic energy change. Energy of motion. Well, as you know, kinetic energy exists, which energy motion, potential energy is like inherent energy.
Ms. Edla,
Yes?
can I please have Shelby read for dismissal?
Thank you.
Thank you.
Shelby, grab this on your way out, because we're going to get to this in a couple minutes, okay? Just one second. Did you grab an extra? Thank you. Okay. So what happens here is, though, you might want to write down this little explanation for yourself. Absolutely write it down for yourself, okay? Though kinetic energy isn't changing, the heat energy is used to overcome something. I'm going to have you guys fill in the blank there in a second, okay? Bye, Shelby. Though kinetic energy isn't changing, the heat energy is used to overcome something that holds molecules together. What am I talking about that holds molecules together? Say again? Bonds are what holds an atom to atom and within a molecule inside. IMFs, intermolecular forces, right? So what's the strongest of the intermolecular forces? Well, okay. Ionic is inside. That's an intramolecular. We're talking about between molecules. So hydrogen bonding is the absolute strongest, which is a form of dipole-dipole. So dipole-dipole in general is the medium one. Who's the lowest force? London dispersion forces. And so, I mean, I can tell you this is an example of water, and water would definitely have lots and lots of hydrogen bonds. So this heat energy is used to overcome IMFs, which holds the molecules together. Because as you can imagine, we're going from a solid, really tightly packed crystal, and we're transitioning to a more fluid situation, and then we're transitioning eventually to a gas situation where it's all spread out. So though the temperature is not changing, we still have to kind of pull them apart. Do you think that's just happening by itself, or does it require energy? They probably require energy because they're attracted to each other. It's not just like, all right, peace, separating, bye. It needs some energy to do that. So that energy here is the heat that's being applied, though the temperature itself is not changing. And it's specifically because of the presence of intermolecular forces. So that's why they're flat, because the heat's still needed, but the temperature's not changing with heat added. Yeah.
So then water would have a lot of heat energy?
Yes, because it has a strong, and that's actually why, it's probably hard to tell, but do you notice that this is a short line, or this is a longer line? Do you guys see that? So that's a really good point. This is just solid going to liquid. You know, kind of overcoming intermolecular forces some, but isn't water still pretty condensed? I mean, it's a liquid. It's still going to be kind of close together. So you overcome like 30% of the intermolecular forces there, but then you go like, woo, your liquid to gas, and it's like 100% separated, right? So that's a 100% overcoming intermolecular forces because it turns to gas, which does require a lot more energy than just a little bit of a phase change with solid liquid. So good point there. Yeah.
On the one video, they talked about like viscosity, like, so if there's more kinetic energy, is there like a lower viscosity?
Less kinetic energy would be moving really slowly and probably relate to a slower moving, like mudslide, like which was viscosity. in terms of like how attractive, it relates to how attractive they are in their kinetic energy, because higher temperature would make it move faster, actually. Yeah, Riley?
Alright, so I was gonna say, like, isn't that called specific heat, like, heat required?
Yeah, so, and we'll talk about this when we get to specific heat again in like 2 weeks. Okay, so I'll ask you to bring that back up, okay? All right, so we're gonna move to gases now, okay? So I'm gonna give you guys about 2 minutes of a break from me. I keep pulling up the wrong slides. And I want you guys to talk about all the variables that you see here with gases. Go. Think of all the variables that can impact gases.
Pressure,
Okay, and I'm going to try my quick demonstration for you about burning papers. Okay, so you guys see this egg? It don't fit, right? No, it don't fit. Okay, we're going to hope that it does eventually. So, what's atmospheric pressure? Okay, well, if we were in our normal atmosphere, yes, it would be 1 atmosphere. It would be 1 atm. What about? This is gross, but we're gonna use my coffee cup. So, what is atmospheric pressure though? Like, don't tell me the value of it.
How the molecules are pressing on the atmosphere.
How the molecules are saying
Like pressing down.
pressing down on the atmosphere. Okay. Do you guys feel that? Why not?
We don't, but
You are surrounded by it. So where is it pushing on you right now? Everywhere? Okay. So if it's everywhere. So where was the atmospheric pressure? If it was pressing, wouldn't it pop the egg out?
it's not top.
Well, how did it push the egg in then, but not before?
Because the fire caused a loss of pressure.
Why would the fire cause the loss of pressure? Okay, so combustion reacts with oxygen. Well, what's oxygen? State of matter. It's a gas, and don't gases cause? They cause what? Gases are tiny particles, right? Tiny particles that bounce around. Those tiny particles bouncing around cause... they have a lot of energy, so they're hitting the sides of the container like crazy. So, you guys read, pressure is caused by... okay, write this down. Pressure is caused by collisions with the container wall. Pressure is caused by collisions with the container wall. So inside of that flask of initially we had this oxygen, right? It was just hanging out, just like a normal atmosphere, doing its thing, hitting inside the container, just like normal. Like it's hitting you in the face right now, it's hitting you in the butt, it's hitting you in the leg. The atmosphere is everywhere. Well, as soon as I put the as soon as I put the flaming cotton ball in there, it combusted, right? And so it was doing what with the oxygen? Eating it. Okay, so consuming it, using it up. So what happened to the pressure inside? It what? It decreased because there was no more oxygen, right? Okay, so why did the egg go in? There was more pressure outside. Well, did we make more pressure on the outside? No, it's just naturally always there. But as soon as we said, a lot of pressure, now we consume all the oxygen inside, there's not as much pressure. The pressure on the outside won, and it pushes it in. It didn't suck it in, it pushed it in. The atmosphere is a vicious thing, okay? Be careful with it. All right, so I only have a couple more minutes with you, so I'm going to have you guys write down this last slide, and then we leave. Huh? You can tell me that tomorrow. All right, write down your givens. These are all the units of gases, and tomorrow we'll actually do the questions. So you need to write down at least the variables. That way tomorrow when we do the equations, you're half a handle, okay? So I will have to unfortunately not give you the homework I thought I was going to give you. That's why I left this here to show how far we get today. You will be doing as much as you can on PS 14, which is just probably the true false. You need to look in your book though. So this is going to give you a good start. Write this down before you go. Do not pack up yet until I see this on your paper. At least the template of it. So these are all the variables of gases, and we'll be using those specifically. So a variable, pressure, volume, temperature, and amount, those are just labels. But the units are really what's important. That's why I have the units delineated here as well. I'll put this up as warm up again tomorrow. Make sure that if you want to take a picture of it, take a picture of it. But we will, I'll take this. I'll need you a chance to look at the mistakes because you guys didn't ask me any questions. Good job today, guys. I hope that you showed your stuff on your stoichiometry. Fourth period will be getting a different test because you guys share too much information with them. Just tell them to study. Like, don't give them an advantage. Some they don't work hard. Doesn't make any sense.
Can I come through for intervention?
I'm doing AP review, so I won't be able to talk to you a lot. So I'll be like really intensely done. Okay, scoot this way. That place to stand. No, bro. William, I've only like 3 lines of notes.
Okay. Can I get a pass? The steward won't believe me, but he'll let me if you.
All right.